Welcome to The Explainer. Today, we're going to talk about the fundamental language of physics. And no, I'm not talking about super complex equations. I'm talking about something way more basic, but absolutely essential. The system that scientists use to measure and literally make sense of our universe. So let's just jump right in with a little thought experiment. Picture this. Two teams of brilliant engineers are building one rocket. Team A works in feet and inches. Team B works in meters and centimeters. What do you think happens? Spoiler alert, it's a disaster. And this isn't just some hypothetical. Mix-ups just like this have caused catastrophic mission failures in the real world. It just goes to show you, shared language for measurement isn't just a nice-to-have. It is absolutely critical.
Right. So, to stop that kind of chaos from happening, science desperately needed a standardized system. And to get there, we first have to understand the problem, which was, for a very long time, we just had way too many different standards. You see, back in the day, it was kind of like the Wild West for measurements. You had different scientific communities using their own systems, like CGS, the British FPS system, or MKS. I mean, sure, they all pretty much agreed on the second for time, but for length and mass, it was all over the place. Trying to collaborate internationally was a total nightmare of doing endless and often incorrect conversions. So let's get down to basics. What even is a unit? Well, at its core, it's just an internationally accepted reference standard. That's it. When we measure something, all we're really doing is comparing it to one of these agreed-upon standards. It is the absolute bedrock of communicating any measurement accurately. So how did science finally solve this mess? Well, they came up with a really elegant solution, a truly universal language for measurement. The big moment came in 1971. The world officially adopted the Système International des Nets, which thankfully we all just call the SI system. Finally, scientists, engineers, everyone had a single global standard to work with. Now, what's so incredible about the SI system is its sheer elegance. Think about it. We can describe our entire physical world, everything in it, using just these 7 fundamental or base units. You can think of them as the primary colors of physics. From these 7, we can describe literally anything. And this is where the genius of the system really shines. Every other unit you can possibly think of for things like speed or force or energy, they're all called derived units. And they aren't new things we have to memorize, they're just combinations of those 7 base units. So for example, speed is just length divided by time. Meters per second. It's that simple. Okay, but just having the words, the units, isn't enough. Any good language needs grammar. And in the language of measurement, that grammar is all about being crystal clear about how precise your measurements actually are. So it all boils down to this one crucial point. A measurement isn't just a number. It's a number that has to carry information about its own uncertainty. When you report a value, you have to give an honest signal about how confident you are in that number, right down to the very last digit. And the formal way scientists do this is with something called significant figures. It's actually a really simple idea. A measurement's significant figures are all the digits you know for sure, plus the very first digit that you had to estimate a little. So if your stopwatch reads 1.62 seconds, you're sure about the 1 and the 6. But that 2? That's your first uncertain but still significant digit. Now, there are a few rules for counting them. Non-zero numbers, always significant. Zeros that are sandwiched in between, they're significant too. But where things get a little tricky and where people make mistakes is with those zeros that are just trailing at the end of a number. Let's look at this case. If a scientist reports a length as 4.700 meters, those 2 zeros at the end are not typos. The decimal point is a deliberate signal. It's telling you, hey, I didn't just measure 4.7. I measured precisely enough to know that the next 2 digits are in fact 0. So this number has 4 significant figures. But now look at this. 4,700 meters. No decimal point. Uh-oh, now we have a problem. Is the real value somewhere around 4,700? Or is it exactly 4,700? We don't know. Those zeros are ambiguous. Are they just placeholders, or were they actually measured? This number could have 2, 3, or even 4 significant figures. It's impossible to tell. And that ambiguity is exactly why scientific notation is a scientist's best friend. When you write the number as 4.700 times 10 to the power of 3, all the guesswork just vanishes. That first part, the 4.700, tells you exactly and clearly that there are 4 significant figures. It's the cleanest, most honest way to communicate your precision.
Now, this whole system, it's not just for writing things down neatly. It actually gives physicists an incredibly powerful tool. It's like a secret weapon for checking their own work, to make sure their equations even make sense in the first place. This weapon is called dimensional analysis, and it's a surprisingly simple but really powerful way to check the basic consistency of any equation in physics. You can think of it as a sanity check. It helps you catch huge mistakes before they ever happen. At its heart is a simple idea called the principle of homogeneity. Now, a dimension is just the fundamental nature of a thing, like length or mass or time, and the principle just says you can only add or subtract things that have the same fundamental nature. It's really just the formal physics way of saying something we all know intuitively. You can't add apples and oranges. You can't add a speed to a force. It's physically meaningless.
Okay, let's get our hands dirty and see how this actually works. We're going to take one of the most famous equations in all of physics, the formula for kinetic energy. K equals 1/2 mv squared. And we're going to see if it passes the dimensional analysis test. First things first, we need to know our target. What are the dimensions of the thing on the left side of the equation? Well, by definition, the dimensions of energy, or K, are mass times length squared divided by time squared. So for this equation to be valid, the stuff on the right side has to have those exact same dimensions.
Okay, let's break down the right side. That 1/2 is just a number, so it has no dimensions. We can ignore it. Mass, m, has the dimension of, well, mass, m. Velocity, v, is length over time, so its dimensions are lt-1. Now we have to square the velocity, which means we square its dimensions. That gives us L squared t-2. Finally, we multiply that by the mass dimension, and we get a final result of m L squared t-2.
And there it is. Look at that. The dimensions on the left side perfectly match the dimensions on the right side. The equation is dimensionally consistent. Now, this doesn't prove the equation is 100% correct. Remember, we ignored that 1/2. But if it had failed this test, we would know for an absolute fact that the formula was wrong.
So we've seen how this beautiful, logical system works, all built on just 7 pillars, 7 base units. It's a language that has allowed science to flourish, but it leaves us with one last, kind of fascinating question to chew on. This system describes the world as we know it, for now. But what happens when we discover something new and fundamental about reality that just doesn't fit into these 7 categories? What then? How does the language of physics evolve?